Hey, what's up, Chem Peeps? What in the heck are we gonna do in this video? We're going to identify a compound as an organic compound and write the formulas and names of basic organic compounds. Breaking it down. Boom! 1. We're going to identify organic compounds. 2. We're going to explain the difference between alkanes, alkenes, and alkynes. Alright, so the study of compounds containing carbon combined with one or more of the elements hydrogen, nitrogen, oxygen, and sulfur, including their properties and their reactions, is known as organic chemistry. Now, before you panic, organic chemistry is a huge field of chemistry unto itself. And we are just going to skim the surface here because you are going to see some organic molecules on the AP Chemistry test. So, what is it about organic compounds that make them organic? How am I going to be able to identify an organic compound from, say, an inorganic compound? Well, generally it comes down to carbon. Carbon. And carbon is unique from other elements in several ways. First, carbon can bond to as many as 4 other atoms. Not many other elements can do that. Bonds to carbon are very strong and often non-reactive. Carbon atoms can attach together in long chains of carbon atoms. Carbon atoms can also attach together to form rings of carbon. If you like it, then you should have put a ring on it, carbon ring. And carbon atoms can form single, double, or triple bonds. So again, as you look to identify organic compounds, you've got to have some carbon involved. And carbon is so awesome and unique for all of the reasons listed on your screen that there are whole semesters and years and majors dedicated to the study of organic chemistry. But again, just brushing the surface. Now, if your organic compound contains only carbon and hydrogen, we call those organic compounds hydrocarbons. Do you see what we did there? Merge together hydrogen and carbon. Hydrocarbons. Now, if your hydrocarbon is a chain and all of the carbons are single bonded together and the molecule is completely saturated with hydrogens, we call those types of molecules alkanes. Boom! Take a look at the example of several alkanes on your screen. Notice that in each case, the carbons are all singly bonded to one another and the chain is saturated with hydrogens. Take a moment, pause the vid, check out the molecular formulas, see how they compare to the structural formulas, and then the ball and stick models. Now, in the event that those carbons aren't all singly bonded together, for example, if you have one or more double bonds, we call those hydrocarbons alkenes. And if there's triple bonds involved, we call them alkynes. Again, they're all hydrocarbons, all just carbon and hydrogen, but depending on the type of bond between the carbon atoms, will determine whether you've got alkanes, alkenes, and alkynes. Boom! On your screen now, you got a bunch of different alkenes. Notice here, you'll find at least one double bond between some of the carbon atoms in your molecule. The molecule then is not completely saturated with hydrogens due to that double bond. Alright, so take a look on your screen and in your note. There's a great overview of alkanes, alkenes, and alkynes. It gives you the types of bonds that are involved, as well as a generic formula to differentiate between the anes, the enes, and the ynes. And I really like that we've got a side-by-side example illustrating ethane, ethene, and ethine. Single, double, triple bond. Alright, in addition to those beautiful carbon chains that are made, many organic compounds also contain carbon rings. And so don't be surprised if you see organic compounds in a ring structure. Benzene rings are really common examples. You can have organic compounds that are not just carbon and hydrogen. Sometimes, in place of those hydrogens that are bonded to carbons, we'll bond something different, some sort of functional group that'll take the place of one of those hydrogens. And that functional group will influence some of the properties of the molecule. So instead of a strictly nonpolar hydrocarbon, things start to get a little interesting. And it is often the functional groups that play a role in the type of intermolecular forces for the substance. And finally, because the functional group is oftentimes what we're focused on to determine the type of intermolecular force, many times we will generalize the rest of the structure with the symbol R, simply used to indicate the continuation of the carbon chain or ring. Boom! For example, sometimes we'll see some oxygens, or sulfurs, or nitrogens. And I don't want you to panic. You'll have all the time in the world when you get to organic chemistry to study and memorize these different functional groups. What I want you to focus on is simply to realize how these functional groups, when you encounter them, will affect the intermolecular forces between organic molecules. Alright, that does it for this vid. Have a fantastic day.